So one of the things that you need to do when you develop a new analysis method or a new analysis model is to verify that the analysis model is actually giving you the information which you think it is giving you. The way you do that is by assuming some structural parameters for a structure that you're interested in. You can simulate the structure, simulate the scattering data. You can then apply your analysis model to that simulated scattering data, and out of your analysis model you get structural information. And now you can compare whether the structural parameters that you get out of your analysis are actually similar to the structural parameters that you put into your structural simulation. So we did exactly that with McSAS. This was still with McSAS1, but since the principle hasn't changed, it will work the same way for McSAS3. So what we did, for example, was to simulate a pentamodal distribution. This means we have 5 populations of monodispersed particles with sizes between, say, 1 and 25 nanometers. We can then simulate what that scattering pattern would look like, and that is shown here in blue. We can analyze it using McSAS. This is shown in red, and we can then find out whether what McSAS gets out is similar to what we put into it. So what McSAS gets out is the size histogram in gray, and that very closely matches the size histogram that we put into our simulation. You can then play around with these things. So instead of having monodispersed systems, we can have polydispersed systems. You know, can we retrieve a quadrimodal but size dispersed size distribution? And yes, it is able to do this. Again, it's not absolutely perfect in the way that it retrieves it, but it is within the uncertainty of the data. So if you improve the uncertainties of your data, it will match closer and closer. Now, okay, well, that's for distribution, so we expect absolutely no problem with just a monomodal distribution. You can have combinations between monodispersed particles and a tailing distribution, or just a tailing distribution, or even a uniform distribution. Now, the uniform distribution is kind of nice because the data that it produces is normally analyzed using a fractal model. So you know, when you have a slope which is not quite a Poirot slope, most people throw a fractal model at it, and that data can also be interpreted by McSAS. What you get out of it is a uniform distribution, which is exactly what a fractal is supposed to be, right? It's a self-similar structure spanning several orders of magnitude in dimension. So these experiments with simulated data and with real data have shown us over the last decade, right? They've shown us a little bit of the information that is present in small angle scattering and the information that is missing, and it has shown us the limitations of analysis. So let me briefly highlight 2 of them. The first one being data quality. Now, if you have measured data and your measured data is quite good, that is fantastic. You can now analyze your data and you can get your size distributions out, just like this example that I show here. It's also included in the example data sets of McSAS3. I think it's the round robin example data set 1. Right, so we have a bimodal distribution, all fine. And now what I can do is I can increase the size of the uncertainties, right? Increase the size of the error bars. And if you do that, you see that gradually the quality of your fit will, or the quality of the result will deteriorate. And that is because McSAS will stop fitting when it has described the data to within the uncertainty of the data. So, of course, if you increase the uncertainty, it will be done quicker, and it will have run fewer optimization cycles. So for McSAS, it is very important that the uncertainty estimates that are on your data are actually reliable, and that the uncertainties are actually reliable, or at least are a reasonable estimate for the real uncertainty of your data. Try and get as close as you can, because the quality of your result depends on it. Now, over the years, we have developed a very extreme version of data correction in our laboratory together with the diamond light source. You can read about it in this paper with the DOI at the bottom left. We are now trying to re-implement this as a Python library to make it more accessible to people. But if you are interested in data corrections, and if you want sort of hassle-free, complete data corrections out of which you get really reliable, high-quality data, feel free to contact me and I'll send you some pointers. Now, the second limitation that we found is that of ambiguity. I can, for a given scattering pattern, fit that scattering pattern assuming we have spherical scatters, and you can see that the fit that we have over here is perfect, right? It's again reduced chi-square of 1, which means that we have on average fitted our data to within the uncertainty of the data. I can change the shape to a cylinder, and I can get an absolutely perfect fit again. The difference between these two is that the size distribution for the cylinder looks like this, and the size distribution for the sphere looks like this. Now, this is just something I quickly threw together, so the distributions aren't really pretty or anything, but you see that the size distributions are slightly different for the two different shapes. But in principle, both are perfectly valid solutions to your scattering problem. Without further information, you cannot determine which one of these is the right one, if there even is such a thing. And that leads us to the following problem. It's really a problem with small angle scattering, in that you have a very limited amount of information, but you want to get more pieces of information out. You want to get information on the shape of the object, and you want to get information on the size or size distribution of the object. And the example above showed that the shape and the polydispersity are inherently linked. So if I change the shape, the polydispersity changes accordingly. There's a third piece of information you would usually want to get out, and that is of packing, inter-particle interference. Do I have particles in, or scatterers in close proximity to one another or not? And in scattering, a good rule of thumb is that you can really only get one of these three, and the other two you need to provide. So if you want to get, for example, the shape of proteins, what you need to do is you need to assume that you have a dilute system, packing disappears, right? And that you have monodispersed proteins, means the polydispersity disappears, and therefore you can retrieve some information on the shape. McSAS assumes a certain packing, a certain shape, and therefore it gets polydispersity. There are other reverse Monte Carlo procedures that assume a polydispersity and a shape, and therefore can retrieve the packing of particles. So I'm pretty sure many of you will not get this reference, but there was in the past a movie called Highlander, and its tagline was "There can be only one." And that is very much the case for small angle scattering. We have a very limited amount of information that we can get out of this. Now, the reason why classical methods seem like there's only one combination that works is because if you have a particular shape, if you assume, say, cylindrical shape, and you have and you assume that the shape of your size distribution is Gaussian or log normal or Schultz, you have thereby fixed the two things which in principle are dependent on one another. So you might only be able to find one combination of shape and distribution shape, which gives you a sort of reasonable solution, and you might then think that that is the solution for your sample. For example, you might say my scattering data only fits to flat ellipsoids with a Schultz-Sim distribution. And therefore, I believe that I have flat ellipsoids with a Schultz-Sim distribution. That is not, unfortunately, the way to go about this. What you need to do is to get an electron microscopy picture to find out what kind of shape your scatterers are in general, and then to find out, and then to use that in your model to find out what kind of distribution works for that. Or you can go from physical principles and go based on physical principles, the only distribution I can have is a Schultz-Sim distribution, and then you try and find whatever shape fits that. But you cannot get both. Now, I am, of course, not 100% correct in that. You know, I can't. I can fit a lot with a lot. Spheres is something that is very universal. I can fit most scattering patterns with spheres, even if the scatterers are not spherical in shape. But that doesn't mean you can fit anything with anything. There is a sort of a unidirectional uniqueness in there, which means I can fit spheres, disks, and rods, rod patterns, using spherical models and different distributions, of course. But I cannot necessarily fit spherical scattering patterns or scattering patterns from spheres using a disk or a rod model. And that has to do with the superposition principle. If I show you the scattering patterns here, you might get a clue about why that is. It's because if I superimpose multiple scattering patterns of spheres of different sizes, you might see that we can fit with that the scattering patterns of all of the others, but I cannot fit. I cannot describe the scattering of spheres by superimposing the scattering from, for example, flat plates. There's no way that you can reproduce that spherical scattering curve with that sloped scattering from flat plates. So the main message here is that when you set up your Monte Carlo models, I recommend in any case to try the sphere model. Sphere model will work in most cases and will give you a clue about the dimensions that are involved in your sample. But before you continue, do take an electron micrograph of the structure in your sample if you can. Find out what shape your scatterers are. Pick the appropriate model, the appropriate form factor, and then use McSAS to find the actual size distribution of your particles. Then you will have basically solved the scattering problem. So good luck. I hope McSAS will make it easier for you to find solutions for this.